Welcome to Epic Lift Systems online training course. This training session will focus on Introduction to Plunger Lift. The intention of these courses is to bring value through the education our team has accumulated over the years in the field and major basins. Not all oil and gas basins are the same, however, the fundamentals of plunger lift remain the same. The topics covered in this course will include liquid loading, well applications for plunger lift, what is plunger lift and how a company could benefit from the installation of a plunger lift systems, the 4 types of plunger lift, optimization of plunger lift systems, troubleshooting existing plunger lift systems, and we will wrap up with case studies and Q&A section. Liquid loading occurs when the well no longer is able to flow or maintain a constant flowing condition, and gas velocity, or gas rate to remove liquids from the wellbore. Why is this? Gas velocities in the tubing has dropped below the minimum requirements to lift liquids from the wellbore. Liquids are falling out of the bottom of the tubing and accumulating. Gas flow is beginning to head, slug, annular transition or flow, which is an early sign of liquid loading. The well has either reached or is now producing at critical rate. Hydrostatic pressure from liquid load can prevent gas from traveling upward and exiting the wellhead. This is similar to use of drilling fluid or salt water to kill a well and eliminate flow when drilling or working over a well. Eventually, the liquid fallback from the natural flowing well will load and log off the well, and an intervention like swabbing or nitrogen may need to be introduced. When the well is below critical rate, liquid fallback occurs from the drag on the tubing walls. This allows buildup of paraffin, salt, and scale. Once the well is at critical rate, it is time to introduce plunger lift system. Some bypass plungers can be introduced when the well is at or right above critical rate. So what you can see here is the liquid fallback from the chart. This chart shows critical rate to lift water from a variety of tubing and casing sizes. As the flowing wellhead tubing pressure increases, the higher the flow rate needs to be to lift fluid effectively. An example with 2 3/8 tubing, if the flowing wellhead pressure is 100 psi, the rate would need to be 350 MCF to lift fluid efficiently. If the rate is lower than 350 MCF, liquid fallback will occur and the well will start to load. If the flowing wellhead pressure is 750 psi at 2 3/8 tubing, the rate would need to be 951 MCF to lift fluid efficiently. And if the flowing tubing pressure was 10 psi at the bottom, the rate would need to be 116 MCF to lift fluid. This is why compression is installed downstream to reduce the flowing wellhead pressure, which increases the volume of gas and fluid that can be produced from the well. This chart shows critical velocity or rate from different fluid rates in 2 3/8 tubing. In general, as the surface pressure increases, the rate will also need to increase, and the more fluid produced from the wellbore means the rate will also need to be increased to evacuate fluid efficiently. Critical rate or critical velocity Turner effect is the minimum velocity required to keep droplets suspended in the moving gas stream so the liquid can be lifted from the wellbore. This value will adjust with changes in surface flowing pressures. A standard cubic foot of gas at standard conditions is subject to higher pressure at the bottom of the well and will have a lower velocity than the same volume at the wellhead where the pressure is lower and velocity is higher. The critical velocity lines at the wellhead and the bottom hole pressure will be close together for shallow wells with higher line pressures, and when there is little differential pressure across the wellbores. These are the types of flow during the life cycle of a well. At the early stages of the well, you'll have mist flow, which is a consistent flow of gas and liquids, typically in newer wells with higher wellhead flowing pressures. And as the well depletes, you'll get into transition flow, which is mist flow with occasional large slugs of fluid. Liquid fallback is occurring and fluid is starting to build up in the production stream. This is typically when bypass plungers are installed. Slug flow are large slugs of fluid evacuating the wellbore along with periods of gas flow. Depending on the well type and the basin, These slug flows can last seconds, minutes, or even hours. Bubble flow is when the well is becoming liquid loaded and hydrostatic pressure is holding back gas. The bottom red line represents the natural decline curve of the well, and the line above is the decline curve if plunger lift is introduced. Using a mechanical interface of plunger as a plunger to dewater the well during the natural flowing state can increase production above the decline curve and even extend the life of the well. Plunger lift can also extend the flowing state of the well before introducing other forms of artificial lift like rod lift. Principles of well pressures. A misconception about plunger lift and really any other artificial lift is that a well needs high pressure to work efficiently. This is not the case. Pressures are very important, but are only part of the equation when implementing plunger lift. The well must be able to maintain or build sufficient lift pressure. Notice I said lift pressure. Lift pressure is the difference between your casing pressure and your sales line pressure. If a well has a packer, then it's the difference between your reservoir bottom hole pressure differential and your line pressure. Lift pressure is often thought of as tubing pressure, but your lift pressure is underneath the plunger. We get asked a lot, well, if tubing pressure is not the lift pressure, then what is it? Tubing pressure reflects the liquid load relative to the lift pressure. If we look at the cross section of the well, we see that the lift pressure is recorded above the plunger and our lift pressure is below. So the casing is used as a storage vessel. By having an open-ended well, gas rises and is stored on the backside. You store gas volume, which helps the expansion or rate while flowing. Your tubing pressure tells you the load pressure of the well's tubing string. Higher tubing pressure relative to the line pressure and casing means less fluid or high gas feed into your tubing, and lower tubing pressure means your fluid is less gas feed in. Now, is there a way to tell if there's enough lift pressure relative to load pressure to lift the plunger? Yes, there is. The rule of thumb is load factor should not exceed 40 to 50% before opening the well. The lower is the better. So load factor equals your shut-in casing pressure minus your shut-in tubing pressure divided by your shut-in casing pressure minus your line multiplied by 100. If your load factor is less than 40%, less shut-in time is needed to lift a plunger. If load factor is greater than 50%, more off time or shut-in time is required. So here's an example with numbers. So your shut-in casing pressure is 500 PSI. And your shutting tubing pressure is 400 PSI. That means your differential pressure is 100 PSI. Your line pressure is 100 PSI. The calculation would be 500 minus 400 to give your differential divided by 500 minus 100 to give your lifting pressure multiplied times 100 equals 25%. Because the load factor is less than the maximum limit of 50%, the plunger and liquid slug should be able to lift when the well is opened. Gas volume is the third principle and one of the most important. A well must have sufficient gas volume because we have learned earlier when gas expands, it creates a necessary expansion or rate needed to lift the plunger. It's important to know what type of well you have before implementing plunger lift. Some wells can be deceiving. Wells can have high pressure but low volume, which cause your plunger to struggle and require more shut-in time, and others with lower pressure but higher volumes relative to field pressures. This is seen with wells with tight shale formations with high pressures but unable to maintain high flow volumes and must be shut in to build pressure to lift the plunger. The illustration shows this gas expansion moving a piston. Gas is compressed, and when decompressed, the molecules expand and move the piston, or in our case, a plunger. The rate in which the expansion occurs all depends on the well's volume capacity. You can imagine two air compressor tanks that are the same size filled with air. One is filled with 100 PSI and the other is filled with 50 PSI. Both tanks have the same size relief valve. If the valves are open at the same time, the tank with 100 PSI will flow longer than the tank with 50 PSI. This is due to the first tank having more volume of gas molecules taking up more space and longer to exit the tank. Basically, the same principle in a gas well. It's the same principle in a gas well. More volume means there's more gas to expand, which helps lift liquids and the plunger. Wells with the packer need higher pressure because the area between the production casing and production tubing cannot be used as a storage vessel, similar to the air compressor and tank example. The industry has basic recommendations needed for gas volumes in wells. So getting into candidate selection for plunger lift. Early intervention would be your bypass plunger candidates. Wells that are operating near critical rate and liquid loading. You have erratic or unstable production. You have gassy liquid wells, particularly horizontal, directional, or shale wells. Paraffin controls, what they're used for as well. And then also in GAPA wells, so gas-assisted plunger lift. It keeps paraffin off the tubing walls, sweeps tubing from any fallback of fluid, and reduces or eliminates injection. Conventional plunger candidates for liquid loading due to unstable rates, high tubing and casing differential, liquid loading indicate, which is a liquid loading indicator. Wells that are currently in some form of intervention, swabbing, intermitting, soaping, or venting. What are the typical solutions in the industry to improve gas production when liquid rates increase? Unload the well to the tank, stop clock, or intermitting, drop soap sticks in the wellbore, install cap strings, decrease flow line back pressure with chokes, well side booster compression, install pumping units, install downhole pumps like an ESP, or install gas lift, or in our case, would be installing plunger lift. This chart shows that there can be a loss of production if artificial lift is not introduced early enough in the well's life cycle. If the bypass plunger was introduced at or above critical rate, the well would not have liquid loaded and would have stayed at or above the decline curve. So why do we use plunger lift? It uses the well's energy, either pressure or gas rates, as a prime mover to lift liquids from the wellbore. There's no need for an external energy source. Efficient seal to reduce the amount of liquid fallback into the wellbore, particularly when the well is below critical rate. Less fluid in the well equals lower bottom hole pressure. It reduces, in most cases, or inhibits scale paraffin formations on the tubing wall, which reduces operating costs. Lowest cost artificial lift method in the industry. And then some ask, why not use just intermitting a well? Well, you lose 10% of your fluid per 1,000 feet when you're just intermitting. So you need that artificial, the plunger as a mechanical interface for artificial lift. What type of information do we need to identify a well if it's a good candidate for plunger lift? We need our tubing pressure, our casing pressure, or flow line pressure or line pressure, produced gas rate, liquid production, oil and water. You know, what is the fluid rate the well needs to produce to stay unloaded, static reservoir pressure, or flowing pressure. Production history is key. Do not rely on a single well test to give the answer for optimization. So plunger lift consists of surface equipment, a plunger, a bottom hole assembly, which is also known as a BHA. So this visual is a well bore, shows a BHA set near the end of the production tubing, and the plunger traveling the entire tubing string above the BHA to the lubricator. The plunger is gas driven from the well and acts as a piston sealing the tubing bore and lifting hydrocarbons to the surface. The major components at surface are the lubricator, which diverts flow from the well bore to the sales line. The spring housing cap at the top of the lubricator has springs to absorb the impact of the plunger and is the access to the well bore for slick line and wire line. We also have a plunger sensor to detect plunger runs, and it sends it to automation or the wellhead controller. The controller, which turns the well on and off through an automated process. You can control differential pressure, time, gas rate, or multiple other pressures. And then some operators also have automation systems built on, so they don't need a controller. You have a motor valve, which allows the well to open and close by the controller or automation. You have a drip pot, which is in place to make sure dry gas is sent to the controller and the motor valve. Pressure regulator is in place to adjust supply gas pressure to the drip pot, controller, or motor valve. These are the three most common lubricator internals that you'll see in the field. This visual shows a cross-section of a Bowen 5K flanged lubricator with a spring housing, internals for a ball and sleeve, a dart, and a conventional plunger. The ball and sleeve internals include an anvil rod, a teardrop, which holds the sleeve up during afterflow. You'll see at the bottom there. A separator rod spring, which for the impact of the ball, and then a shock spring for the impact of the plunger. One thing to note, if you're ever wanting to pull your ball and sleeve, to get the ball out of the well, you need to pull the striker rod, and then when they come up, they won't separate, and you'll be able to close your master valve and get them both out. The dart internals include an anvil, a dart rod to shift the bypass pin of the dart, both a separator rod spring and a shock spring for the impact on arrival. And then a conventional internals include just an anvil and a shock spring for the impact of a plunger with a fishneck on it, whether it's conventional or even a center rod plunger. There's no need for a rod in a conventional style plunger because these plungers do not fall against flow, and we don't need to shift any rod or bypass. The bottom hole assembly equipment consists of a bumper spring to absorb the impact of a plunger on the descent. The spring can be set in the vertical section of the tubing or within the curve of the horizontal. The spring is set in the tubing with one of the following adapters. First is a hold down with a 1, 2, or 3 cup option to set in the seating nipple within the tubing string. The hold down threads to the bottom of the bumper spring, seals off between the outside diameter of the BHA assembly and the ID of the tubing, diverting flow through the inside of the hold down to control fluid. The collar stop is designed to be attached to the bottom of the bumper spring assembly and hold the BHA within a collar gap. A tubing stop is designed to be attached to the bottom of a bumper spring assembly and hold the BHA in the tubing string using locking dies. One thing to note, if you're wanting to retain fluid above the BHA assembly with a collar stop or a tubing stop, a pack-off assembly must be included to seal between the BHA assembly and the tubing walls. A collet is used to latch equipment with a fishing neck like a collar stop, tubing stop, or other bumper springs. A standing valve can also be included in BHA. A standing valve is a check valve with the bumper spring assembly. A ball and seat standing valve retains the fluid above the bumper spring, so fluid can be effectively evacuated from the tubing string by a plunger. When the well is flowing, the gas flow lifts fluid through the BHA and the standing valve to prevent fluid from falling back through the BHA when the well is turned off. A pressure relief standing valve can also be installed in the bumper spring assembly. The pressure relief standing valve is activated at different pressures, typically 40 psi, to balance the fluid load in the tubing to efficiently deliquefy the well on each plunger run. The pressure relief standing valve can also act as a safety feature. If you want to kill the well, you can pump through the bumper spring. On a standard standing valve, you're unable to do that. The tubing and casing can also be equalized through a standing valve if necessary. A pressure relief standing valve is necessary. Now let's get into how to select a plunger. This visual shows the types of plungers in a life cycle of a well. Moving from left to right, bypass plungers like ball and sleeves and darts are introduced early in the life cycle of a well at critical rate. As the well volumes and pressures decrease over time, the well needs more shut-in time to build up pressure. Different bypass plungers with reduced ports will be introduced. If the well needs 30 minutes of shut-in time or at least to build up the well to lift the plunger, then a conventional plunger is introduced for optimal seal and lift as much fluid as possible in each plunger run. If the well has reached the end of its life cycle for conventional plunger lift, a multi-stage plunger lift system can be introduced. So getting more into continuous or bypass type of plungers and early intervention, these are installed on free-flowing wells. These plungers are installed because they need minimal shut-in time and have the ability to fall against flow if the bypass ports are large enough. These plungers are lifting multiple small loads of fluid per run to relieve hydrostatic pressure to maintain high flowing volumes, consistent differential pressure, and low flowing bottom hole pressure. Limited shut-in time for these wells also reduces stress on surface equipment, compression, because There are a lot, not large bursts of gas being sent during shut-in or after being shut in for an extended period of time. It is recommended to use a quality bumper spring when using these type of plungers because of the impact on the bumper spring and the fall speeds. Conventional plunger overview. These are installed gas rates less than 70% of surface critical. The well requires shut-in period to build pressure to overcome low gas velocity. And the seal between the plunger and the tubing walls is important to reduce slippage. This is efficient intermitting. So getting more into multi-stage, so this is if we're at the bottom of the life cycle of the well. Multi-stage plunger lift is designed to stage fluid into two sections. The stage tool is set 40 to 60% into the tubing string. There's a plunger that runs from the BHA to from the end of tubing to the stage tool. There's another plunger that runs from the stage tool to the surface. The multi-stage tool has a standing valve to retain fluid above the tool during shut-in. So these are designed to partition the well's fluid and load per cycle, reduce shut-in time comparison to a single stage well that requires pressure build because the plunger travels half the distance. So reduces extended shut-in time for casing buildup. Some candidates for these types of wells would be wells that require extended shut-in period, usually 2 hours for a conventional plunger. High tubing casing differential, which means well is liquid loaded. A single conventional plunger has inconsistent or missed arrivals due to fluid load. A single conventional plunger has slower than recommended arrival times, less than 500 foot per minute, and a well would periodically require unload to get the plunger tripping. So next we'll discuss the plunger cycle process of plungers. So the motor valve is closed to stop the flow from the wellbore down the flow line. Since the flow is stopped, the plunger begins to fall from the lubricator at surface to the bumper spring. We'll discuss different fall speeds later in this presentation. The well is shut in at surface, so the formation begins to pressurize the casing and tubing while the well is closed, and the plunger is making its descent. The calculation for off time depends on is the depth of the bumper spring divided by 200 foot per minute, which is the minimum off time. Please note, this may need to be extended for wells with larger fluid columns because plunger will fall closer to 40 foot per minute through fluid, or even if a plunger is falling through a deviated section because we'll have fluid plus drag on it as well. Once we have allowed an adequate time for the plunger to reach the bumper spring, and there's enough time for the well to pressure up to lift the plunger and fluid column, the well is opened up. This is called the lifting or plunger wait or on time. The controller or automation sends a signal to the latch valve, which opens the motor valve, which turns the well on. Head gas that was on top of the plunger evacuates the tubing and sent down the sales line. So you'll see a spike in gas when it opens up at first. At the same time, the plunger begins to descend, lifting the fluid above it to the surface. The pressurized gas in the annulus expands into the tubing and lifts the plunger and fluid above it. An efficient plunger speed while lifting is 650 to 750 foot per minute. The fluid acts as a shock absorber and cushions the plunger impact in the lubricator. The plunger sensor reads the plunger once it's passed through the lubricator and sends a signal to the controller or automation for successful plunger arrival. The well then switches to afterflow cycle. During the afterflow cycle, the plunger is held in the lubricator from gas flow below, exiting the wellbore down the sales line. Downhole fluid is transitioning from the formation to the annulus and up the tubing. The longer the afterflow period is, the more fluid that accumulates in the tubing for the next plunger run. We need enough of fluid in there to cushion the impact of the plunger on the BHA, but not too much. The next plunger run stalls out. We want to adjust our plunger or adjust our afterflow so our next plunger run is 650 to 750 foot arrival window. During the afterflow process, you will also see tubing pressures drop and typically run right above line pressure, and the casing pressure will begin to increase, which indicates liquid loading is taking place downhole. If the well flows out too long after this point, you may load up and the plunger may stall out on the next run. Once we have an adequate amount of afterflow time, the controller automation sends a signal to shut the well in, and the plunger begins to drop, and the sequence begins again. So a seal is very important. The seal of a plunger is what keeps the fluid from falling back and allows our gas drive or critical rate to move the plunger to surface. As a plunger travels up and down the well, the seal begins to wear off, which decreases its seal efficiency. This is noticeable in production volumes and plunger travel times. Lower volume wells, or wells that do not build up much of a load factor, should opt to use the best sealing plunger possible. This is to effectively evacuate as much fluid as possible from the tubing string during the plunger trip. Plungers are built for specific tubing sizes and should be inspected and replaced when worn. A plunger must also fit within the API OD drift tolerance as well, otherwise the plunger will not fall to bottom. Now we're going to get into rules of thumb for LGR, which is liquid to gas ratio. The maximum of 150 barrels per million MCF. Now, some larger wells and horizontals, you can lift a lot more fluid than this, but this is just a rule of thumb for basic plunger lift. A plunger can only lift a certain amount of hydrostatic fluid weight to surface. To lift more fluid, a higher reservoir pressure and/or lower surface pressure is required. Back pressure, change in pressure between casing and tubing pressure shut-in should not exceed 40 to 50% difference between casing and sales line. Lower is better. Because the well must be shut in to build pressure to cycle the plunger and fluid to surface. Not having a packer is best, but plungers can operate with a packer in the hole. Annular communication will help reduce the amount of shut-in time required to cycle the plunger. Packer completions can have a hole punched into the tubing above the packer and a B valve installed to ensure plunger arrivals. Gapple systems typically have packers, however, we're referring to conventional gas drive from the formation with these rules of thumb. Rule of thumb for conventional plungers cannot affect a rule of thumb. A conventional plunger cannot effectively lift more than 150 barrels per million MCF liquid to gas ratio. Also, a rule of thumb is a bypass recycle plunger cannot effectively move more than 100 barrels per million MCF liquid to gas ratio, or LGR. They can be installed earlier than this just to make sure the tubing stays clean. This is because liquid fallback from the plunger seal of the OD in the bypass area. If the well is producing 15 barrels of fluid a day at 200 MCF, the LGR would equal 75 barrels per million MCF. So it'd be 15 barrels per day divided by 200 MCF times 1,000 to get us a million MCF equals 75 barrels per million MCF. Therefore, based on the LGR, this well is a candidate. Note, LGR ratio is based on 100% water cut. If oil is present, the ratio can safely be raised to 175 barrels per million MCF. So we're getting into pressures. Rule of thumb, we talked about this earlier, but this is the load factor should not exceed 40 to 50% before opening the well, so lower is better. To find our load factor, we look at shut-in casing minus our shut-in tubing divided by our shut-in casing minus our line times 100. And then I'm not going to go through it again, but we are at 25%, which is less than 40. So we'll be able to lift the plunger and the fluid to surface efficiently. Now we're going to dig into different types of bypass plungers. These plungers are installed as early intervention, critical rate or just below critical rate in the well, slug flow or high rates, used for paraffin control and high liquid volume wells. Wells that have on-site compression where extended shut-in time would risk killing compression or fuel gas. Existing plunger wells, a standard or other bypass with 60+% more flow time during the day. Gas lift applications to keep paraffin from ports, valves, locations, and increase overall liquid removal per cycle. reduce injection or eliminate injection, compression rental. Ball and sleeve selection is dependent on the gas and fluid rate in the well. In general, high rate wells have longer sleeves and heavier balls, and the opposite for lower producing wells. Another option for bypass plungers is a dart. Well applications for a dart plunger are free-flowing gas lift wells in early intervention stages of liquid loading, moderate to high production volumes up to 200 barrels per day. Light paraffin or solid control, because there's a clutch at the bottom there, we don't want to fill that with solids. Controlled fall speeds and reliable clutch in wet and gassy conditions. Needs very little shut-in time, less than 5 seconds to fall, as long as the bypass ports are large enough. It does not need afterflow to fall against flow. No separation. Clutch keeps bypass area open. Another option for a bypass plunger is a center rod plunger. It requires minimal or no shut-in. One benefit from this is you don't have to have a striker rod or a stinger in the lubricator. So you can run it with a conventional style lubricator setup. There's a larger tolerance between the bypass function. So if you have more solids, sand, salt, things like that, it's going to run a little bit better than maybe a dart. Multiple bypass options to fit well characteristics as well. Now we're going to get into different types of conventional plungers. First is a pad plunger, most commonly run plunger. It's high efficiency. It's a metal to metal friction seal against the tubing walls. The spring loaded pads, there's springs behind the pads that push out to the tubing walls, but they can collapse if there's a tight spot in the tubing or an anomaly. Keeps tubing walls clean from solid buildups, and you can run these as with a single, double, or triple pad, depending on the amount of fluid production in the well. Solid plungers, also known as sand chaser, bar stock, clean out, rotary plungers. There's different names in the industry. These are actually the lowest efficiency because they have a turbulent seal, but they work well with solids, sand, salt, wax, and they're very durable. One thing to note is you can implement a bypass option with these too, where you have ports in the top so you can fall a little bit faster than a conventional solid. To make that transition between a bypass and a conventional plunger. We can also have rifling or special cuts or different ports for sands, removal of sands, rotation and deviated wells, things like that. Next is a brush plunger. These are high efficiency wet seal. But the brush does wear out quickly. So these are more designed for sand, clean out plungers, but also they have a great seal, but they will wear out fast. Where we have issues with them is below, or when temperatures are higher than 250 degrees, bottom hole temperature anyway. And then also if it's a high gas rate, it'll blow the bristles off of it or make it weak. And it also does not collapse more than 15 thousandths. So these are general fall speeds for different types of plungers. First, the fastest falling plunger is a two-piece plunger, which is a ball and sleeve. And then, like I said before, you can have different weights of balls and then different lengths of sleeves that make them fall faster. The next step down will be the dart plunger, and then the center rod plunger for fall speeds. So what you can see here is the two-piece, the dart, and the center rod will fall against flow at different rates, and depending on their port sizes, they'll fall faster with larger port sizes. And then as the well shut in, or when the well shut in, it'll fall faster because they're not falling against flow. But conventional plungers like a sand plunger, pad plunger, brush plunger will not fall against flow. So when the well is selling, they are coming up or staying up in the lubricator. They will not fall if the well is turned back on. So now we're going to get into plunger operations. Proper plunger lift optimization requires experience, knowledge of liquid loading and flow characteristics, and most importantly, patience. Some wells may take days to line out and others may take less than that. Just because a plunger is running does not mean the system is optimized. It takes minimal effort to make a plunger go up and down. Operators must evaluate more than just the cycles. Arrival time, speed is critical to optimizing a plunger lift system. Plunger lift optimization requires a combination of consistent plunger cycles, adequate drawdown of the well, steady production on the well's natural decline curve, and optimal total gas rate to optimize the gap pull system. When optimizing your plunger cycles with an EPIC controller, the A stands for arrival and the F stands for failure or a missed run. The goal is to have all cycles in arrival and to have their arrival times consistent and at safe travel speeds. So just because we're making runs doesn't mean they're the most efficient runs. We want to make sure there's fluid on top of that plunger. The ideal travel times for a conventional plunger is 650 to 750 foot per minute. You do not want to exceed about 800 feet per minute, or it could cause serious damage to the plunger or surface equipment. This ensures that your gas rate is above critical rate, you're bringing fluid up, and the plunger is not impacting the lubricator too hard. Each well has an ideal travel time and can be calculated by the following formula. The bumper spring depth divided by 650 feet to 750 foot per minute. So an example is if we have a 6,500 foot well, to find it at 750 foot per minute, we divide it and we find it's 8.7 minutes of desired arrival time. Now, if we do 6,500 foot well divided by 650 foot per minute, that would be 10 minutes. That means our arrival window needs to be between 8.7 minutes and 10 minutes. Bypass plungers can change this calculation because they're falling against flow and typically making round trips during the lifting time. So we may see double sometimes depending on the rates and what it's falling against on the arrival time. Arrival times can highly influence production rates as well as equipment preservation. Each cycle should be consistent with fluid load on top of the plunger before arriving. Cycle times should be consistent as well, with typical times being within 1 minute plus or minus of each other. Now, deeper wells will have a larger spread on that. So if you're trying to lift from 15,000 feet compared to a well that's at 3,000 feet, it's a little different. There's a lot more variables that go into lifting a plunger. Arrival and failures should be logged daily to ensure proper optimization. If you're experiencing slow arrival times, which are arrival times slower than 600 feet per minute, do the following. Be sure to reduce restrictions like chokes, orifices, and other debris within the sales line causing a restriction. Use the best sealing plunger possible in wells that experience slow runs. Also make sure the plunger is not worn out. Make sure you are not experiencing irregular high line pressure. Reduce your afterflow time and reduce the amount of fluid entering your tubing. At a last resort, increase your shut-in time to build up pressure to build more lift pressure or better the load factor. Fast cycles are typically the opposite. Start with reducing your shut-in time for less load factor and lift pressure. Try to go to bare minimum if possible. Make sure the plunger is reaching the bumper spring though, because we want to make sure we have a fluid load on top of it. Increase your afterflow time and draw the fluid into the tubing on each run. You may need to add a standing valve to help with this, to retain the fluid within the tubing if your well is producing less than 10 barrels per day. And then swap to a faster falling plunger if needed. This may reduce your shut-in time between plunger trips. Routine plunger inspections are a must for proper optimization. It is highly recommended to replace a plunger once they reach a wear threshold. You may notice that your production volumes or cycles can be off when your plunger is worn. It's recommended to pull and inspect a plunger at least once a month. Some wells that have sand or high corrosive environments may require every 2 weeks. Bypass plungers and solid plungers have wear indicators at top, middle, and bottom. If these are worn flat, it's time to replace the plunger. Pad plungers, check the wear indicator on the compression of the pads. Brush plunger, check the brush along the side and on the sides of the plunger as well. Brush plungers usually don't last more than 1.5 to 2 months, so they may need to be inspected every 3 weeks. You should look for uneven wear or severe scarring on the side If it's wearing out too fast, plungers also tend to wear on one side and deviated well bores. Electronic troubleshooting usually involves the controller and the rival sensor. When you're having issues with the controller not opening and closing 8 out of 10 times, it's because of the latching valve inside the controller. The controller should have 25 to 35 psi of dry gas supply to function properly. More supply could cause the valve not to shut, or also serious damage to the components, and not enough gas can cause it not to open. There may also be a plug or a freeze in the gas supply or the latch valve itself. Battery issues, usually related to wiring issues within the solar panel and not charging the controller. Check all the wiring, make sure there's nothing making contact that shouldn't be, and make sure everything's in the proper spot when the wires are inserted, and make sure you have plenty of voltage, with the ideal range being from over 5.9 volts. The latch valve is the heart of the plunger lift operation. It is the most delicate hardware in the field and needs to have a clean, dry gas supply sent to it. If your latch valve is not functioning, your well will not turn on and off. If fluid gets into your supply, you will need to purge the line and clean inside the latch valve and oil for smooth operation. In cold climates, it is key to keep liquids out of the lines to prevent freezing in the latch valve. The major components of the latch valve are the solenoid. It's a magnetic actuator that opens and closes the internal valve, and the poppet and sends and stops gas to the motor valve. The tube, which houses the poppet. The poppet is a spring-loaded plunger that either allows or blocks gas from going to the motor valve. And then also the solenoid will actuate, and the magnet moves the poppet up and down the tube. You should hear the solenoid clicking. If it's clicking and you're not seeing the valve open or close, you want to make sure you don't have a plug in your line somewhere, and you're not getting, because that means you're probably not getting gas supply to send to your motor valve. Rival sensor troubleshooting is pretty straightforward. If you're having issues with your sensor not detecting a plunger, first remember there's a 30-second delay on a controller, so it will not detect anything before 30 seconds. Make sure the plunger is actually arriving and not in the lubricator, or the well is not loaded up. Check the wiring of the arrival sensor and the controller. Make sure there are no loose strands of wires making contact with anything other than the terminal. Check the battery voltage and check that there is power to the sensor. To make sure the sensor is working properly, switch the controller or automation to on time, lifting time, or plunger weight, and run a material made of steel similar to a plunger next to the sensor to check to see if the plunger arrival registers. Make sure you also wait 30 seconds if that's what your system requires. For false or fast plunger detections, again, make sure the plunger is not caught in the lubricator. Check to make sure the plunger is not running that fast. You have to be able to be at the well. Check for wiring and power on the controller. The sensor may need to be replaced if in contact with large bursts of electricity like a lightning. Other things to look for when inspecting: you want to look at your top spring in your lubricator. You want to see if it's encased or exposed. Either way, you need to make sure that the spring is not collapsed, cracked, or broken. Downhole spring inspection and frequency. You want to make sure you're setting up a preventative maintenance on the springs, whether it's 6 months or yearly. That's what we recommend, but make sure you have a system in place for that. Motor valve is working properly, or if it's leaking, to check this for check to see if the well is selling when the valve is closed. If so, the trim and seat may need to be replaced. The well needs to be fully closed for the plunger to fall. So if the trim and seat is leaking, it's going to give you issues with your optimizing your plunger system. Other things to look for as well: is your sensor detecting accurately? Are there leaks at surface equipment? You also want to check all your O-rings, your lubricator, and your caps, and things like that. Also, good practice to check your threads, flange connections to see if there's any strains or stresses. Next is a plunger retrieval tool. So these can be dropped to retrieve a plunger that's stuck down hole. Tool is designed to latch the fishing neck of plungers, or there's also option of a magnet plunger. Drop tools are usually brand specific, so make sure whatever you're trying to fish out, test it at surface to make sure it's actually going to latch that tool before you drop it down home. And then do not use with the striking rod in the cap. 30 to 60 minute drops is standard unless using the bypass version. A soft arrival at surface ensures longer tool life. Make sure you're at the wellhead and be able to throttle the flow and ready to close the master valve quickly once the retrieval tool arrives. Now we're going to get into some case studies of positive results from plunger lift installations. Lift Systems currently has more than 10,000 plunger lift systems running worldwide. Our success is due to the result operators have experienced and the value we bring from increased production and reduced costs from other forms of artificial lift. This chart shows a 13 well package. 13 wells were installed, or plunger lift was installed on these 13 wells. There was an increase in production of 1.28 million MCF per day. Total cost was $195,000 for these 13 wells, which comes out to $15,000 per well. The return on investment has been greater than 100%, and the payout was 1.5 months. Now, one thing to think is once you already have the surface equipment, the bumper spring, all that, all you're replacing is the plunger. The cost, benefits to the cost is definitely much better over time. This chart shows a well that was struggling from liquid loading. The plunger lift system was installed, production was increased, and now it's back above the decline curve. When a well is deliquified with the plunger, it will run more consistent and not liquid load as often. This is an example of removing a cap string for artificial lift and installing a plunger lift system. The plunger acts as a mechanical interface to effectively lift fluid from the BHA to the surface. And as a result, we see an increase in production and deliquification of the well. This chart shows the production increase after installing a plunger lift system. If the plunger was installed 6 months prior, there may have not been a dip in production from liquid loading. This is when the plunger lift's installation can pay for itself pretty quickly.